Hi, I'm Shreyas Pandey, Senior AI Engineer at Microsoft. Today, we are going to design the next generation autonomous workflows by building AI agents. As part of this course, we'll see what AI agents are and the foundational pieces that they are composed of. We'll also take a look at how can we augment the abilities of these AI agents so that they can solve real-world complex problems. We'll start with building our very first basic agent and incrementally augment its abilities to take real-world actions. We'll also take a look at how we can augment the agent's abilities to expand its knowledge base so that it has more than the word knowledge and can use domain-specific knowledge as well. Lastly, we'll take a look at how can we build systems that comprise of these agents collaborating together to solve real-world applications. By the end of this course, we should be able to grasp what are the foundational pieces of modern Gen AI systems and these agents. We should be able to also implement our own first agents with cutting-edge tools. We should be able to learn how to augment these agents' abilities with memory and tools so that we can build sophisticated applications on top of these. And lastly, we should be able to design and orchestrate multi-agent systems that can solve really sophisticated problems. Let's start this discussion with foundational models, which are the backbone of modern generative AI. These are large language machine learning models, which are pre-trained on huge amounts of data through techniques like self-supervised learning. This means they learn from raw, unannotated data, capturing general forms of text and images so that they have the general sense of the word knowledge. For example, GPT-4 is a foundational model that underpins many text generation tasks. Similarly, DALL-E is a foundational model that can generate images from text. Essentially, these foundational models form the basis on which many sophisticated AI applications are built. So the next question obviously is, how do we interact with these models? So for that, we have an inference layer. Typically, how these models work is by predicting the next token. You can think of tokens as subwords or parts of images. So they take a sequence of tokens and try to predict the next token. And they are able to do this because they have been pre-trained on huge amount of data and have a general sense of word knowledge. When this inference repeats iteratively to generate a complete body of text, that is when you have a complete response coming out of the LLM. Many AI service providers implement this functionality and expose these as APIs, which are completion APIs. But you have challenges with these completion APIs because the next word prediction is based on the sequence of token that you provide. And the way you end your input basically decides the quality of response that you are going to get out of the system. Now, it's a challenge because that's not how typically we chat with the AI systems or any system in general. To overcome this challenge, they have exposed chat completion APIs, which basically simulate a more natural conversation-like flow, which is composed of questions and answers, where you can ask a question to the AI and the AI responds back using an answer. How they typically do is they have role-based messages so that you have system messages that decide the persona or the guidelines that the AI has to remember when it's responding back. Then you have the user messages, which basically put forward a query or pass some context which is needed by the LLM to respond. And finally, the assistant message that comprises of the response coming out of the AI system. So in essence, these chat completion APIs are tailored for back and forth conversations which simulate a real-world chat app. But to build next-gen systems, we have to look beyond and augment the AI's abilities to take actions, take into account word knowledge that it's not been trained on, and basically be a domain expert. To overcome all these, we have the concept of agents, which encapsulate all these building pieces together so that we can build complex real-world applications on top of that. In summary, foundational models provide the core capabilities upon which you can build layers of applications, ranging from your inference APIs all the way to these agents, and transform this raw innate ability of next token prediction into something that is usable for solving real-world applications. So before we dive into agents, let's look into the chat completion APIs in depth. This is essential because these are effectively the APIs that lend the reasoning power to these agents. So as we discussed earlier, these chat completion APIs are themselves built on the inference capabilities of these foundational models. What that means is these APIs are also stateless in nature. So you have your system prompt along with the user prompt, which then feeds into these models, and ultimately the LLM generates a response. Now, if the user needs to ask a follow-up or you want to continue the conversation, it's the duty of the consumer to basically feed in this chat history so that the whole context is maintained for the length of the conversation. In this way, the consumer can keep passing the whole context as a collection of messages, and they can effectively continue the conversation until the user requires so. So let's talk about AI agents on a conceptual level. These agents are comprised of three main building blocks. One, which is the reasoning engine, which we'd already talked about. These can be completion APIs, themselves powered by these foundational pieces. Then you have your knowledge base or memory, which lends domain-specific knowledge to these agents. This can be medical-related information for medical assistants, travel-related information for travel assistants, and so on. And lastly, we have tools, which can either be used to gather more information, which can be real-time and so on, or they can be used by these agents to take actions in the digital world that they are performing. So to summarize, the agents are made of these little building blocks, which together gets encapsulated into an AI system that has the ability to gather more knowledge, have domain-specific knowledge, and then finally act on that knowledge in the real-world examples. Now you may wonder how these agentic systems are different from the traditional AI workflows. So in a typical traditional AI workflow, which is modeled as finite state machines, you have different states and transitions defined on those states. So they are very stringent in that respect, very rigid, and they cannot be dynamically updated. Whereas coming to these agentic workflows, since all the decisions, all the transitions are decided by AI at runtime while you are processing that request, they can dynamically adapt to various inputs, and basically their decision making is governed through a series of dynamic things. Thus, through multi-step reasoning and flexible orchestration, they are capable of adjusting their own orchestration and basically model it as per the problem. Now that we have looked at these agents on a conceptual level, let's see how do you go about building one. On an implementation level, these agents consist of four main building blocks. First are the agent themselves, or the configuration of these agents, which basically has the instruction set that lends the personality that that agent uses for domain-specific knowledge. Then next, you have threads. Threads are a stateful way for managing context throughout the conversation. You can think of them as a collection of messages where they truncate automatically so that the content fits into the context window of the model. Then we have tools. Tools basically augment the abilities of LLM, one, to gather more knowledge, and two, to take specific actions. Thus, they can be broadly categorized into these two buckets. Your knowledge tools could be, the ones which gather information from a database, from web search, and so on. And the action tools are something which let the model connect to an external API or run code through code interpreters, and so on. Then we have the concept of runs. Runs are basically these fundamental objects that lets you glue all these three pieces together. So you have your instruction set as part of agent config, and you have your state managed as part of threads. A run is a function of these agents and these threads, which ultimately leads to a response generation at the end of that step. So effectively, you can have your run 1, which takes the configuration defined as part of your agent A, applies it to the context contained in your thread T, and at the end of the run, you'll have an updated thread which will contain the response generated during your run 1. Similarly, you can have your run 2, which basically takes the updated thread now, which has been augmented by the response of the previous run. You can have another agent A2 work on that. In this way, multiple agents can share context as part of the same thread, which lets them collaborate together. Now, one may naturally ask, why agents? Amidst multiple reasons, there are two reasons that stand out. Number one, encapsulation. Basically, agent encapsulate all these building blocks together through a glued layer and gives us logical entities to deal with so that we can model real-world problems using those. Secondly, they are robust and reliable because of their self-correcting, dynamic, and iterative nature. This dynamic adaptability lets them perform better even in unprecedented scenarios. Let's build our first agent. Now we have a lot of different options that we can choose from when selecting one to build our own agent. These range from open source SDKs all the way to managed services provided by cloud providers. So when choosing the right tool for your particular use case, you should remember that some of these allow for more control but come with more overhead in terms of the lines of code that you need to write even to bootstrap a simple agent. Others, which are not so flexible, are fairly convenient to use and fall to the extreme right end of this spectrum. Some of the options that are available are LangChain, AutoGen, and services, managed services like Azure AI Service, and so on. For this lab, we are going to use OpenAI agents, which are fairly simple to use. For this lab, we are going to build our first agent, which will be a flight agent responsible for fetching real-time information about flights, and we'll try to augment it with tools that let it do so. So let's build our flight agent grounded using web search results. We'll start with the necessary setup and imports. We are using two main SDKs, which are the OpenAI ones for basic client connections and the Agent SDK, which is the new launch from OpenAI, which encapsulates all the necessary helpers for bootstrapping an agent. Then we create an OpenAI client using the OpenAI key, which basically you can supply as part of your environment variables. Let's start creating the basic flight agent with web search step by step. First, we need to import the web search tool, which is a native tool available as part of the Agents SDK. This is the same tool that powers the ChatGPT web search results, which you see in the application. First and foremost, we start by configuring the agent instructions. The instruction is itself divided into multiple sections, as you can see. Firstly, we start with giving the agent a persona by giving it a role. So we specify that it's a flight travel expert whose sole focus is on planning flights. Its task is to generate detailed flight plans based on user preferences and budget. Then we provide guidelines to it as to what needs to be included in the flight plan. This includes duration, exact cost, airline, etc. We also scope the problem down for the flight agent and limit its jurisdiction only to focus on flights. So we explicitly tell it that you should not be considering hotels or any other things apart from the flights. Then we also tell it explicitly that it needs to ground its results using the web search tool. And then we have additional instructions as part of it. We mentioned that it needs to handle missing information if the context is not provided by the user, and also that it should maintain a professional tone because it's an agent typically operating in hospitality sector. Then we come to bootstrapping the flight agent. As you can see, we provide the name of the agent, the instruction set, which we defined above, the handoff description, which is a description of this agent pertaining to the capabilities of these agents. And this will be used, let's say, if another agent chooses to delegate tasks and pass control to our flight agent. Then most importantly, we also specify that it has access to the web search tool, which it can determine to use if necessary. Next, we have some basic model settings, which has parameters like maximum tokens. In other words, these are the maximum tokens that have to be used while generating a response. For our example, we have limited it to 10,000. So our response cannot have more than 10,000 tokens. But if your model supports so, you can keep altering with this number. Then we have temperature, which basically dictates how creative the model gets to be. So higher the value of temperature, the more creative the model is. Then we have some other settings which we can play around with, but we'll not go into detail in this lab. Then one of the parameters is, of course, the tool choice. As you can see, we have opted for the value auto, which means that the model gets to determine at runtime whether a particular tool has to be invoked or not. Some of the other values for this feature is, of course, when you have to enforce the tool call every time. Basically, you can ask the LLM to always have the tool call irrespective of the query, and it becomes fairly deterministic. Right now, we have opted for auto because we want the flight agent to take its own call when deciding whether it needs to search the results from the web or not. So this sets up our basic agent. Next, we move to the user query. So I have a simple query here where I want to fly from Hyderabad to New York, let's say on 15th April 2025. And I specify the budget, which is $1,000 in my case. And hopefully by asking whether it can find me a flight, I'll get the results that I desire for. I'll get the results that I want. Then we have some helper functions to run this particular query using the flight agent that we have constructed above. And as you can see, the response includes, 3 options for me. One from Qatar Airways, and it has all the necessary details that you would consider when, looking for flight options. It also gives me a link as to pointing to the reference or the source from where, it has fetched this particular information. And similarly for the other 2 options. Now, the key thing to note here is, if you notice, I asked it to book a flight which is of a future date. Normally, as you may know, LLMs have a cutoff date, meaning that their word knowledge is constrained to that particular date, and that's the date that they have been last trained on. But with web search results or web search tool in particular, you basically augment the LLM's ability to fetch real-time information, for example, in this case, pertaining to flights. Now, while this response is good, in typical cases, you may want to take this functionality and either tie it to an UI element or basically use it to call an external API to actually book those flights. This textual output cannot be directly passed to do so. So let's see how we can enhance our flight agent with structured outputs so that the final response is parsable and thus can be used with external APIs as well as with code. So firstly, we import the base model and the field constructs from the Pydantic library. Next, we try to construct an output schema for our flight agent. Let's call it flight details, which basically encapsulates all the necessary properties that you may want in the output pertaining to a single flight. This includes departure airport, departure date and time, arrival airport, and so on. Next, we create an Uber level class, which has a list of these flight details because ultimately we want multiple options from this flight agent. Then we keep everything else the same. The instruction is the same, the tool is the same, all the model settings are the same, as you can see. What we additionally do here is basically we provide the output type for the flight agent, which lets it know that the final response has to be tied to this particular schema, which we have specified above. And with the same query, you can see that we get results which are schema bound and follow the necessary structure that we desire out of the system. What this lets us do is probably parse it, plug it to an external API, plug it to an UI element, or use it however we want. So in our very first lab, we created our very first agent, which is the flight agent. We augmented that agent with web search tool that lends it the ability to look for flights in real time. Then we saw how we could use structured outputs to get schema-bound responses out of the LLM, which lets us plug it into an external API or an UI element if needed, which basically makes it parsable for us to use. Now that we have figured out how to recommend flights using real-time data, probably let's see how we can accommodate hotel suggestions also as part of our travel plan. For that, typically we would need to rely on a hotel database that we can somehow plug into our LLM so that it can make use of it while creating the travel plan for us. The idea to go about that would be create a database specialized for retrieval using not just only keywords, but also similarity-based searches. These are typically known as your vector databases. This basically takes 2 major steps. The first step is, of course, creating the database before even you start processing the query. In this step, you'll have your knowledge base or a series of documents which get chunked into smaller pieces. These pieces are then convert it to their numerical representations using embedding models surfaced as embedding APIs, which ultimately land into your vector databases. What your vector databases typically allow is searching for these vectors directly. So when you fetch a vector, you essentially get that chunk of that document. Now we get to step 2, which involves the actual processing of the query. So whenever a query comes, the idea is to enrich that query with supporting chunks of documents so that LLM has everything it needs to answer that query, right? For that, the query itself is then converted to its numerical representation or embeddings using the same embedding model that we used to create the vector database in the first place. And when we have that vector embedding, we basically compare it against all the chunks, rather all the vector embeddings of those chunks, and fetch the most relevant ones using cosine similarity or similar logic. Once we have the most relevant chunks retrieved from the database, we take the query and these chunks and combine them together to form the prompt that has everything, hopefully, that the LLM needs to answer these queries. This is called RAG, or Retrieval Augmented Generation, where you fetch all the relevant chunks of documents from a wide array of data sets and have that supplemented with the query, which enables the LLM with all the information it needs to basically answer that query. Now let's build our hotel agent that uses a vector store to fetch the hotel options from a database. So the first step is to create and set up our vector store. As you can see, this is a single API call through the OpenAI client where you provide the store name and it creates a vector store for you. We have provided the store name as hotel directory for this one. As you can see, the result indicates that the hotel directory vector store has been created, but currently it does not have any file. So let's start uploading the hotel data to this vector store. For this lab, we have the samples hotel data that contains a bunch of options for hotels that we want to ingest into our vector store. Now let's upload this file to our vector store. Again, it uses a single API call to create the file and then one to attach it to the vector store that we just created. As you can see, the request has been accepted. Next, let's see if the file has been successfully added or not. So we fetch the vector store details and we find that it contains a file which has the completed state. Let's try to query our vector store and see if we are indeed getting the results that we have just ingested. So I have a sample query here which asks for boutique hotels with jacuzzi. I make the search to that particular vector store and I have limited the maximum number of results to 3. As you can see, I have fetched 3 results, the 3 most relevant results in fact, and it also shows me the matching score for each of these. We talked about that how the query would first get converted to the vector representation, and then it will be matched against the vector representation of the chunks which we have just ingested. So the 3 most relevant chunks that we fetched as part of this query, which lists, a cozy tub, are these 3, which we can see in the results, along with their matching scores. As you can see, all of these would contain jacuzzi. Next, let's enable our hotel agent to make use of this vector search so that it can provide hotel recommendations that are grounded into the search results. For this, let's import the file search tool that the hotel agent can leverage for finding accommodations using the vector store. Again, we start with the instructions first, where we provide the role to this particular agent, which dictates that it's an hotel agent, that lets users find the best accommodations as per their requirements. We provide certain guidelines to it. That's what are the things that it should include in the response: star rating, amenities, cost, and any other relevant hotel details. Then we basically scope its jurisdiction again to only focus on hotels so that it doesn't go recommending flights, restaurants, etc. We explicitly mention that it needs to ground its results to available hotels that we are supplying as part of the directory ingested in the vector store. Next, we also ask it to maintain a professional tone because it's one of the agents that is operating in the hospitality sector. Next, Let's see how we can bootstrap our hotel agent. So we provide the name of the hotel agent. We provide the instructions that we just defined above. We provide the description of the agent in case another agent needs to invoke this and hand off the control to it. Then as part of the tool list, we provide the file search tool, and we also specify which vector store needs to be used in order for the hotel agent to leverage the directory that we just created. Lastly, we have some model settings, and I have kept the temperature lower in this case because we want to strictly ground the results based on the database that we have provided. So our hotel agent is bootstrapped. Next, let's start querying the agent. So I start with a simple query where I specify that I'm traveling to New York, looking for a boutique hotel to stay for 3 nights. And as an additional point, I specify that I should be able to make my coffee in my own room, and I have a budget of $1,000. Then using this query, we run the hotel agent, and here are the results. So actually it found me 2 options, and the cost of, let's say, this one, which is TECH City Hotel, is $150.99 per night. Let's actually see if that is indeed the case in our sample data. So this is the TECH City Hotel, and it has found me a room which costs $150.99 because it has the coffee maker. So there were other options, but it was intelligent enough that the room which matches my requirements is particularly this room, which costs $150.99 per night. And then it's able to calculate the total cost for 3 nights, which comes out to be $452. And it says that it matches my budget requirements, which I had supplied as $1,000. So working as expected. So in this example, firstly, we created a vector store. Then we created a sample file of hotel directory, and then we uploaded it and attached it to the vector store. Then we attached that particular vector store to our hotel agent, which enabled it to invoke it at runtime and get the hotel details supplied in the hotel directory. In this way, we can supplement an agent's knowledge base with our own domain-specific knowledge that the agent can retrieve at runtime through retrieval augmented generation and use it in its own responses. This is one of the easiest ways to basically increase the word knowledge of your agents. So far, we have built our expert agents, one specializing in flights and the other in hotels. Each of these agents have their own unique set of tools and knowledge bases that lend them the capacity to go about their tasks. Now, in a typical human-operated travel agency, customers would go with their set of requirements pertaining to their budget, constraint in terms of the number of days they want to spend at that particular destination, and so on. And the travel agency would typically take care of all of these and accommodate that in that travel plan. So let's see if we can take our AI travel agency to the same level and make use of these individual bits and pieces to create a comprehensive travel plan for the end customers. For that, we leverage a multi-agent system where we have a manager which delegates tasks to these individual expert agents, which comprises of the flight agent specialized in booking flights and the hotel agent, specializing in booking hotel accommodations, and see how we can cater to users' requests across all these agents collaborating together. In order to implement this and see this in action, we have to consider 3 main pieces. The first is, of course, the selection criteria of an agent. So whenever the travel manager gets a request, it should decide intelligently which should be the next agent which should take up the processing of this request. Next, it should also determine if all the agents collaborating up until now have been able to achieve the user's goal, and it's time for the turn to terminate and the response to be sent back to the user. Thirdly, it should also decide that how we manage context across all these 3 different agents. So let's see this in action by going into our third lab. Let's start building the orchestration system, which comprises of these specialized agents that we have built up until now, and the manager agent that orchestrates these agents together so that we build a complete plan for the end customer. Firstly, we create the manager agent. we again start with creating the manager agent instructions. We start by giving it a role so that it has a persona now to act as a travel manager, whose responsibility is to create and validate a trip. Upon receiving a user request, we ask the manager to coordinate with that team of agents that it has access to so that we generate a plan consisting of travel and flight options. We specify the responsibilities of these agents, which is basically determining which agent has to be selected next. And secondly, to determine if the turn is complete and the response is good enough to be taken back to the user. In other words, that the user requirements have been met. We then specify the guidelines for the manager to approve a particular plan. We specify what are the conditions for the plan to get approved and also the negative scenarios which the manager should not approve a plan if they exist. And then, of course, we provide the budget considerations so that the recommendation out of the AI system always takes into account the budget that has been specified by the user. So with this comprehensive prompt, we go and create the manager agent. We use structured outputs so that the response coming out of the travel manager is parsable in code and we can create a workflow around that. So the structured output is simple. It just contains 3 parameters. One is to indicate whether the plan has been approved or not. In other words, whether the user requirements have been met or not. Then the detailed response or the comments from the travel manager based on the context that has been accumulated so far. And then the next agent, which should pick up the task of processing the request. With this, we create the manager agent. Notice we have specified the output type to be travel plan details because that is what we are parsing at the end of the day to build a workflow around the complete system. So again, we start with the query, which is a comprehensive query now. Up until now, we were asking about flights and hotels individually. But as you can see here, we have now queried the system about both hotels and flights. And we have also increased the budget to $2,000 because possibly that is what you need if you want to travel to New York for 4 days. And then we have asked it to create a comprehensive travel plan. Then we start building the flow, which will enable the travel manager to 1, select the next agent, 2, determine if the turn is complete, and if not, delegate the task to the next agent. So it's a simple for loop for now, which runs until the plan is approved or the next agent keeps getting selected. If the next agent is flight agent as determined by the manager, we select that. If it's hotel agent, we select that and ultimately run that particular agent. And finally, after these individual specific agents or the specialized agents have been invoked, we take that thread back to the manager and see that all the requirements have met or not. If they haven't been met so far, we continue to execute the loop where the manager gets to pick the next agent as to what has left so far. And ultimately, the hope is that the plan will get approved and we'll have something that meets the user's requirements and the response can be taken back to them. Next, the manager still determines that the plan is not ready to be taken back to the user because it contains flight details, but the hotel details are yet to be figured out. So it selects the hotel agent next to basically take up this context and start executing. The hotel agent then again acting on user requirements. The hotel agent comes up with the hotel recommendations for the user's stay in New York, given their requirement for a 4-night stay. Then after this, the manager determines that the plan has been approved as now it includes both the information for the flight and the hotels, and it also checks whether it fits in the total budget. And since it lists down, individual cost prices for both flights and hotels, and their sum is less than what the user had asked for as part of the budget, it determines that the plan is approved and the response can be taken back to the user. So in this way, we saw that how a dynamic system adapting based on user requirements can make use of expert agents to weave a plan that can solve complex problems and cater to complex requirements that the user may have. So in this way, we can mimic a real-world use case of travel planning agency and achieve it using a group of agents. The best part probably about this is nothing of this is hard-coded, and all the steps are determined dynamically by the travel manager based on the context that has been received from the user. We started this discussion with foundational models, the ones which form the core capabilities of modern GenAI systems. Then we talked about the inference APIs, where the next token prediction happens based on the knowledge accumulated through pre-training. Then we talked about how to interact with those inferences through completion and chat completion APIs. We saw the challenges with those and how they are limited to just Q&A. And whenever you want more out of your AI systems, you probably need to start looking at something which is more sophisticated. And the answer to that was agents. Agents encapsulated memory, tools, and the reasoning engine in form of these foundational models and provided us better ways of building real-world applications. We also looked at these agentic systems which are dynamic and can adapt to user requirements in a better way as opposed to traditional AI workflows which are fairly rigid. Next, we saw how to build these agents ground up using some of the cutting-edge technologies. We started this journey by building our very first agent, which was responsible for booking flights. And it could fetch real-world information because we augmented it using web search tool. Next, we looked at how we can expand the knowledge base of these agents by connecting them to vector stores. These vector stores are very powerful because they can support semantic querying, that is, querying based on meaning rather than just keyword matching, which makes them suited for building LLM applications. Lastly, we saw how we can glue these pieces together into something which is more comprehensive using multi-agent orchestration. We saw how we can manage context across all these agents. We also looked at techniques for configuring your manager such that the next agent is selected dynamically, and also putting an approval strategy in place so that we can ensure that the output going out of the system back to the user has been approved by the manager. This dynamic encapsulation of these agents working together lets us build really sophisticated applications. The design patterns and code pieces that we developed as part of this lab is fairly extensible and can be applied to n number of real-world problems. Few of them being appointment booking for doctors, restaurant booking, code generation and review, and whatnot. Thank you for watching this. All the best for exploring this next generation AI building pieces. Good luck.